Okay, today we're going to look at the Pythagorean theorem and trigonometry. We're going to look at adding radicals, the Pythagorean theorem, and then we're going to introduce the study of trigonometry, which is the study of right-angled triangles. So last time we learned how to multiply and divide radicals. And with radicals, what we're trying to do is we're trying to simplify a radical down so that we're just left with something that cannot be taken the square root of. So let's have a look at this. It's asking us to find the perimeter of a triangle with lengths 4 root 3, root 12, and root 75. So if we have a triangle like this, and this side is 4 root 3, and this side is root 12, and this side is root 75, we want to find the perimeter, which means we want to add them all together. So we have 4 root 3 plus root 12 plus root 75. But the problem here is we can't just simply add things that have different radicals. You cannot add what's inside the radicals. You have to have the same radical for each expression to be able to add them together. So what I'm going to try and do is I'm going to try and simplify these radicals as much as I can. 4 root 3 cannot be simplified because it cannot take the square root of 3. Well, let's have a look at the square root of 12. The square root of 12 is the same thing as 4 times the square root of 4 times 3. And 75 can be split up into 25 times 3. Now these are all good numbers because I can take the square root of 4 and I can take the square root of 25. So I'm left with 4 square root of 3 plus, well, the square root of 4 is 2, so it'll be 2 root 3 plus, and the square root of 25 is 5, so I have 5 root 3. And I'm going to treat the root 3 like an x. So if I had 4x plus 2x plus 5x, well, that would be 11x. So my answer is simply just 11 root 3. Now I'm going to try and add the perimeter. I'm going to try and find the perimeter of a triangle with lengths 3 root 5, root 20, and 2 root 45. So I'm not going to draw the triangle this time, but we know what to do. We want to add them all together. So I have 3 root 5, root 20, and 2 root 45. Root 5 is already in its simplest form. I can't actually split 5 into anything other than 1 and 5. So I'm going to leave 3 root 5 by itself. 20, well, 20 is the same thing as 4 times 5. Now you may be noticing a pattern right now. What I'm trying to do is I'm trying to find the 5 inside each of these radicals. So here I'm going to do the same thing. I know that 45 is the same as 9 times 5. And once again, this is good because I can take the square root of 4 and I can take the square root of 9. So I get 3 root 5 plus, well, the square root of 4 is 2. So I have 2 root 5. And finally, the square root of 9 is 3. So 3 times 2 is 6 root 5. So I'll repeat that last step because it's really important and sometimes quite difficult to grasp. This 2 is on the outside here, so I'm saying 2 times this radical. So when I take a 3 out of here by taking the square root of 9, I need to do 2 times 3, which gives me 6. So I'm left with 6 root 5. Now just like the last problem, I'm going to add all my terms up on the outside of the radical. So I have 3 plus 2, which is 5. And 5 plus 6, which is 11. So my answer is 11 root 5. Pythagoras. Pythagoras lived over 2,400 years ago in Greece. He was one of the greatest minds the world has ever seen. And he even developed a secret society with a single desire to understand the universe and the gods through geometry. If anyone were to share any of the findings, they would be killed. At best. They would often be tortured, forced to reveal who they shared their secrets with, and then they too would be killed. The greatest achievement of Pythagoras and his society was the Pythagorean theorem, which is used in architecture and engineering even up until today. But it's more than just that, it is a beautiful, beautiful proof. So the theorem is if you take the square of the legs and add them together, you will get the square of the hypotenuse. So that's a squared plus b squared equals c squared. So what we're going to do is we're going to look at this right triangle here and notice that we've drawn the altitude. Once again, the altitude connects the right angle to the hypotenuse perpendicularly with a line. So we have a right angle here. And once again, we know that CDB is congruent to ACB, and we know that ADC is also congruent to ACB. So all the triangles are congruent to one another, and we're going to use that in the proof. I also want to note that C here is just the same as this leg x plus this leg over here y. So C is equal to x plus y. So now I'm going to use a little bit of clever ratios in order to come up with the formula. Well, I have right here x and a. So x is the medium side of the medium triangle, here CDB, and a is the hypotenuse, or the longest side. So what I'm going to do is I'm going to make this ratio x over a is equal to, so once again I took medium side over big side. So now I'm going to look at the biggest triangle. The medium side of the biggest triangle, which is ABC, is a. Then I have to take it over the longest side, which of course is C. I'm going to leave this ratio alone for just 1 second. I'm actually going to do the same thing with a couple different sides. I'm going to pick y over b. So y is the smallest side of the smallest triangle, and b is the largest side of the smallest triangle. And I'm going to relate it back to the biggest triangle again, ABC. And I have that b is the smallest side of the biggest triangle, and c is the biggest side of the biggest triangle. If this feels confusing at all, I would recommend watching this over a couple of times. This step is absolutely crucial in the proof. So now I'm simply just going to cross multiply. So when I cross multiply, my c goes to the top on this side, and my a goes to the top on this side. So I get xc is equal to a squared. Then down here I'm going to do the same thing with the cross multiply, so I'm going to bring the c up to the top over here and the b up to the top over here, and I get yc is equal to b squared. Now we're starting to see some familiar things from what we want to prove in the theorem. We have a squared plus b squared is equal to c squared. So let's go ahead and add them together. So I have a squared plus b squared. But that's simply just equal to, from this last step, xc plus yc. But look at that, they actually both have c in common, so let's factor out a c from both of them. And I get c times x plus y. But x plus y is just the same thing as c from up here. So I get c times c, which is equal to c squared. And there you go. The most important theorem in all of geometry is that simple. So now we're going to look at a completely new topic called trigonometry, which is the study of right triangles. The reason we study right triangles is because they're actually really nice, and it turns out that they actually have a lot to do with circles, which we'll learn a lot more about in Algebra 2. So trigonometry is the study of relationships in right triangles. So let's have a look at the parts of a right triangle. So if I were to call this angle right here alpha, and the only reason I'm calling this alpha is to differentiate from the fact that there's an A right here. And I'm just going to call this side over here A, this side over here B, and this side over here C. Then I call this side over here, if I were to draw a line from the angle out, that side I hit right here, side A, or you could call it side CB, we're going to call this whole side the opposite, because it is opposite my angle alpha. And then we know the longest side of a right triangle is the hypotenuse. And once again, the opposite is equal to CB. And then the hypotenuse is equal to AC. And then the final side, which is kind of an awkward one, we're going to call the adjacent. Which is equal to AB. Now all these sides are all in relation to this angle A, or alpha. If I were to make an angle C, it would be different. AB would be the opposite, because that's the side opposite. The hypotenuse would stay the same, and then CB would be my adjacent. It's really important to note we're talking about an angle here. We're not talking about a certain triangle. So let's have a look at these two right triangles. They look very similar, and we want to show, well, are they in fact similar? Well, we have that they both have a 90-degree angle, and they both have the angle 32.9977. So by the angle-angle criterion, they must be similar. So we have EFD is similar to triangle ABC. And the reason this is important, or maybe relevant to us now, is all we need to know is one angle of a right triangle, and then we can say a lot about all triangles with that same angle. So now we can relate the angle to the sides. So there's something called SOHCAHTOA, which you may or may not have heard of before. It stands for sine is equal to the opposite over hypotenuse. Cosine, this is ka, is equal to the adjacent over the hypotenuse. And TOA, which means tangent, is equal to opposite over adjacent. And sine is actually a function, which means you put something into it and you get something out. Sine, you will put in an angle, like 30 degrees for example, and then what you get out is the ratio of the opposite of hypotenuse for any right triangle with that angle. So for example, if we take this triangle here, let's say that this side is 3, this side is 4, this side is 5, and you were asked to find the sine of angle A, and let's say it's alpha, we have the sine of alpha is equal to, well, the opposite of alpha is 4, and the hypotenuse, of course, is just the longest side, which is 5, so sine of alpha is 4 over 5. How about cosine of alpha? Cosine of alpha is equal to the adjacent over hypotenuse. The adjacent is just the other side. It's kind of difficult to figure out what the adjacent is until you found out the opposite and the hypotenuse, and it's just the one left over. So we have that's equal to 3 over 5. And then finally the tangent of alpha, which is equal to the opposite over the adjacent. So that is 4 over 3. Okay, so our final topic is complementary angles. We have an angle here, alpha, and we have an angle here, beta. Now the interesting thing is if we look at sine of alpha, that is equal to the opposite of the hypotenuse. So the opposite of alpha is BC. So that is side BC. And the hypotenuse is AB. So it's the side AB. But now let's have a look at the cosine of beta. So the cosine is the adjacent over the hypotenuse. So the opposite for beta is AC, and the hypotenuse is AB, which must mean the adjacent of beta is BC. The hypotenuse is always just the longest side of the right triangle, so that, again, that's AB. So we've just shown if you have one angle of a right triangle alpha and another angle of the right triangle beta, that the sine of alpha has to be the same as the cosine of beta. Using exactly the same logic, we can also show that the sine of beta is equal to the cosine of alpha. Not only that, alpha plus beta must be equal to 90 degrees, and this is because alpha plus beta plus the right angle 90 degrees is equal to 180. And if you minus 90 to both sides, these 90s cancel, and then you're left with alpha plus beta is equal to 90 degrees. And we're going to use all this information to solve the following problems. So if you know the sine of 20 degrees, what do you know about the cosine? So what cosine relates to the sine of 20 degrees? This must be equal to the cosine of something. Well, let's say this 20 is our alpha, and we want to find cosine of beta. Well, we know that alpha plus beta is equal to 90. We know that our alpha is 20, so 20 plus beta is equal to 90. We minus 20 from both sides. And then we have that beta is equal to 70. So this must be equal to the cosine of 70. The second problem is a little bit more involved. So we have our alpha is the Greek letter theta, which we use to designate an angle, and we have beta is equal to theta plus 30. We have that alpha plus beta must be equal to 90. But alpha plus beta must also be equal to, well, theta, as that's our alpha, plus theta plus 30, which is our beta. So this is equal to 2 theta plus 30. So we have 2 theta plus 30 is equal to 90. So we have 2 theta is equal to 60. I just minus 30 from both sides here. So dividing by 2, we get theta is equal to 30. So right here I have sine of 30 is equal to cosine of 60. And that's that for this week.